Okay. Well, I mean, let's start. Um, First of all, one of you guys emailed me about semaphore implementation over the weekend. I think I need to clarify a couple of things um, on the actual semaphore operation implementation. So in a class, oops. So in the class, I talk about this implementation, the implementation on the top, okay? So essentially, there are different implementations on semaphore, down and up operations. The differences are rather minor, okay? So let's first see the down logic for what we put in the lecture slide when I gave the lecture on this. So basically, here, the logic on the top is first it would decrement the semaphore, right, integer value. If the value becomes less than 0, after decrementing, it would add the calling thread or process to a wait queue and block the calling thread or process. Now, this implementation can have semaphore value go below 0, okay? So this implementation actually um, this implementation actually is popular in many operating system and semaphore library implementations. So if you look at the logic, like in the bottom half of the screen, um, this is the logic that is described from Tannenbaum modern operating system textbook. Okay, so this implementation is, you can see the logic here. It first checks if the semaphore value is greater than 0. Okay, if so, it would decrement the semaphore value. Otherwise, it would add the calling thread or a process to a wait queue and block the calling thread or process. Now, this in the implementation in the bottom half, you cannot have the semaphore value actually less than 0. Okay, so that's that's this implementation. It's just minor difference here between these two different implementations. I would like to say these two they're used in different systems in different libraries. The key here is with either one of these implementations, if the semaphore value starts from 0, okay, the calling thread would be blocked after calling down operation. Okay, we use that. We use a semaphores initialized as 0, and we use that kind of a scheme for enforcing scheduling constraint. Right? We talk about many examples in the class, but I just want to say these two, they're essentially the same. Okay. Because some of you actually read the textbook. Again, the textbook is with this implementation. So, so this was the example I talk about in the class, right? I have I have process A that would wait for process B and C and D to execute first, and then process A can continue, right? So with either implementation I just talk about, you could achieve this, the scheduling order. So anyway, I just want to talk about this, in case some of you actually read the textbook that got confused about this. All right. All right, so let's start the class for today, which will pick up where we left off from last class. All right, let me see. All right, so last class we started talking about the file implementation, essentially uh, the core subject that we need to talk about in the file system subject. So we started with this contiguous allocation scheme, right? So you know the files would be given consecutive blocks, right? So so we lay out files with contiguous um, blocks of space on the disk or on the solid state drive. Now while this contiguous allocation can give you probably the optimal efficiency in sequential and direct access, but this is a bad kind of idea because the external fragmentation will eventually make the disk unusable, right? So here it's similar to memory allocation when we talk about, you know, as files come and go, you know, as files get created, moved, deleted, you know, you could end up with a lot of fragmentation on the disk. That would eventually make the disk unusable. And also this scheme is bad for handling the growth of the files. If you have file size growing, and then this scheme is not good to handle that scenario. So then we move on to the linked list allocation scheme. The linked list allocation is essentially, so basically it reserves part of the block. Uh, so here, like every piece of the block is a physical block on the disk, okay? So you would reserve part of the block to contain the block number of the next block, right? So essentially, you have a sort of a header here that has a pointer to the to the uh, to the to the next block, right? So you end up with a series of pointers, right? That would track all the blocks that are allocated to the file, right? So with this scheme, we talk about, you know, no space would be lost to disk external fragmentation, and except for internal fragmentation in the last block, right? So you could still have some uh, uh, wasted space that in the last block, okay? So, but with this linked list scheme, do we see any issues here? You know, so first, you know, like first, let's see from the storage efficiency perspective. The amount of data storage in a block is actually no longer a power of two, because the pointer, right, at the beginning takes up a few bytes, right? So so you have a pointer here that would take some space, although it's very trivial. But this with this, you know, the many programs, they like reading and write in blocks whose size is a power of two, actually. So with the first few bytes of each block occupied by a pointer to the next block, reads of the full block size require acquiring, you know, and concatenating information from two disk blocks, you know, which generates extra overhead due to the copying. So this is not ideal. So what could be other problems with this scheme? So yeah, anybody can tell me what could be another problem with this scheme? Let's say, you know, if we consider the access efficiency, right? Sequential access or direct access, what could be a problem here?
If you're trying to access like one of the middle blocks, do you have to like iterate through the whole list or even like the ones at the end?
That's correct. Thank you, Blake. Yeah, that's exactly right. So essentially, yeah, you would have to traverse, right? Let's say you want to access the last block, right? You would have to traverse the whole uh, linked list, right, to be able to access, to figure out where that last block is, right? So you can say the direct access or random access could be extremely slow, right? So we're talking about traverse this structure on the disk, actually. So because where do you save that? All these blocks, they're saved on the disk or solid state drive. So you have to traverse this linked list actually on the disk to be able to find out any position in the file, right? Right. So if the blocks are dispersed across the disk, it would incur horrible performance, right? Um, so so that's a major downside of this scheme. Okay, so based on this, what could be a possible improvement based on this scheme, right? So maybe we can try to solve this by moving the links to an external data structure, right? So we're talking about the link here, the pointer, right, between blocks. So people came up with an improvement idea for this. This is what we call file allocation table. Okay, so essentially it's a variation of linked list. It's a faster version of linked list. So rather than putting all these pointers, right, in the physical blocks, right? So we could extract these pointers out and put them into a separate data structure, what we call file allocation table. Okay? All right. So now this FAT first I would like to talk about. So this is actually a popular, was actually used to be a popular file system implementation in the early versions of Windows. Actually, it is still popular nowadays. Actually, in small media storage like flash drives, like SD cards. Um, so so again, the basic idea here is to use a separate table to store and track this linked list chain of the file block information. Okay. Now by the way, here, each file block here normally has the size of 1K or 2K or 4K. Okay. We talk about disk as a device. We call the disk as a block device, meaning when we read or write, when we interacting with the disk, we don't read by the units of bytes. Okay, we read by the unit of blocks. Okay. All right. So this is how it works. So this is the file allocation table. Let's see how this actually works. Okay, so essentially, let's look at, so we have two files here. Okay, let's look at file A. This is file A. Okay, so you can see it has what? It has a physical block 4, 7, 2, 10, 12. Okay, you can see here 4, 7, 2, 10, 12. Now let's look at this table. So it starts from here. It starts from here, right? So file A starts from physical block 4, right? And what is in this table? What does this entry at index 4 remembers. Right? It remembers the next block number. Next block is what? Is 7. Okay, so it remembers 7, and then you can you can go from 7. You traverse this to the 7th entry in this table. Then you find the next block number would be 2, right? And 2 is the physical. Again, each entry remembers the physical block number. Okay, so 2 would be this, right? So, and you goes to 2 and you find 10 there, right? So that would be the next physical block number. And you go to 10, okay? And while then you find block number 12 is put in the in this entry. So you go to the 12th entry in this table. Then you will find -1. -1 is essentially the end of file. Okay, so this is how you chain the pointers, right, together in this file allocation table to find out all the physical blocks for a particular file. All right, I guess this is straightforward. All right, so so what are some advantages, right, of using this scheme, right? So with this kind of implementation, first, the pointers are not stored as part of the block anymore, as I talk about, right? So that's an improvement, right? So using this organization, the entire block is available, right? I mean, the whole, so this table actually remembers everything, right, for your file allocation. All right, so let's look at, you know, so let's look at from the access perspective. So for sequential access, you know, you start from the beginning and you read the file along. So that's really it's not bad, because this is essentially you have the whole. Normally, you load the whole FAT table in the memory. Okay, so essentially you traverse everything. You know, you traverse this table in the memory. So that wouldn't be too bad. Okay, so sequential access, actually, I just talked about the sequential access. Okay, you just follow that chain of pointers. What about direct access, random access? It's not bad either, right? Because again, it should be much faster, because what? Because this whole table is now in the memory. Okay, so we're not traversing the linked list on the physical disk anymore. Okay, that's the key difference here between the FAT and the linked list. The original linked list implementation. This whole table again is stored in the memory. So operating on the memory would be faster, right? So all right, so as I put here. So, well, I mean, the random access, if you use the computational complexity, the big O analysis, and it's still, it still requires ON kind of a traversal time, right? But again, this is in the memory, so that wouldn't be too bad, okay? Now, there is like a major downside of using this is that it could take a lot of memory, right? Just for storing this table, right? And because you would need to have the whole table inside the memory. And also, usually you want to duplicate this table because of, like as a redundancy scheme for some kind of you know, safety measures, because if you lose this table, and you just essentially you lose everything, right? Your file system would become corrupted, right? So usually you make a duplicate of this table. If one copy goes bad, the duplicated one can be used. again, so let's see, how big this table can be, if you have a large disk size or large partition size. So we just talked about the FAT table could be very big. So here the trade-off you made is to trade space for access performance, right? As compared to the pure linked list. So if you have a large partition, let's see how big the FAT table could be. All right. So let's say you have a 10 terabytes kind of drive, okay, with each block having 4 KB kind of size. All right. So how many blocks are there, right? So you simply use 10 terabytes, right? Divided by 4 KB, right? This is the number of blocks you would have, right? With this kind of with 10 terabytes partition, right? So let's say for each for remembering each block location, you need what? You need 4 bytes, okay? Unsigned integer 32 would be 4 bytes, okay? Let's say, here, right? So each entry, right? Each entry in the FAT table takes 4 bytes, right? So essentially that's a pointer, right? To remember the location of the block, right? So you have these many blocks, right? So what would be the size, like overall, just for remembering all the pointers to the block? It would be using this number of blocks times 4, right? 4 is what? 4 is like 2 to the power of 2, right? So then you will get essentially this number, okay? So this would be the size of a FAT table, okay? So your FAT table is really fat, actually. It's 10 gigabytes. Just for this table, 10 gigabytes just for remembering the FAT table. All right, that's not ideal. It's just you have 10 gigabytes used just for file allocation information. All right, and this FAT table size would be what? Would be proportional in size to the partition size. Okay, as the partition grows larger, this table grows linearly with the partition size. All right. So, so that was a downside. So we talk about the robustness of the FAT table. It has some problems there also. Recovery from corruption is difficult, right? Again, that table, if it's corrupted, you're in trouble. So that's why usually you want to duplicate the table. All right. Okay, so that was FAT, right? Which we don't really, it's not really used these days anymore. Again, there's still, it is still popular in small storage kind of drives, okay? Why is that? We just talk about it, right? So if you have a small size of storage, then the FAT table size wouldn't be big either, right? So then FAT still works. All right. All right. Let's move on to the file allocation scheme that we want to study the most. Okay. For the file system implementation. Okay. So it's called index allocation. I kind of briefly mentioned this scheme in the beginning of the file system class. Last class. So let's look at this more advanced file allocation scheme. It is actually used in a lot of real world file system design. okay? Mostly in the Unix systems, Linux systems. Your Mac OS is also using this. Well, check that. Mac, like actually, Apple has its own proprietary Apple file system. Actually, it's more or less also based on this, okay? So, all right, and actually Windows NTFS also adopted this same approach. All right, so what's an index allocation? Okay, so essentially each file has a root index node. It's called inode. Okay, and it's this inode index node is actually a file descriptor data structure that contains file metadata. Okay, you know what is a file metadata? It's the description of the file, right? Which include general file information, you know, file attributes. File attributes may include, you know, like last modified by, you know, you know, all kinds of other attributes, you know, like security information like owner of the file, permission to access the file. So basically, those are file metadata. Last class, I showed you guys a list of them. So basically, this inode is essentially the data structure that contains all those information. And so that's the file information part, right? And also, this inode has a collection of disk addresses of the files blocks. Okay, so the inode remembers has a collection of disk addresses of the files physical blocks. Okay, so these are pointers to the blocks. Again, so it's similar to the linked list, but actually it actually remembers the pointers for all the blocks, okay? As compared to the linked list, you have to, you know, you have to traverse, right? You have to traverse the linked list to get the information of where each block is located. Here in this inode, you start from the root node, and usually the root node has some direct pointers to some physical blocks, and at the end it has a pointer to the next inode for extension. Okay, so so typically here the number of direct pointers of physical blocks. So here I have 1 second here. So typically, so I have, right, and direct pointers, right? So typically in a Unix implementation, n here is like around 10, okay? So, so if each data block, and in Unix, each data block is usually 1K size, okay? So if you have 10 blocks here, right? What would be the file size, right? That would be 10K, right? Right. So if you have 10 direct pointers, that means the 10 direct pointers will give you a file size for 10K, right? And this design actually is specifically considering what we talked about before, is that usually most of the files you have in your system, they're small files, all right? So with this design, it's sort of like it favors small files. So you sort of like kind of estimate most of the files in your system, they're within 10K, okay? So the majority of the storage space is actually occupied by a small number of large files, okay? So your system, so most of the files for describing them, you only need like one level of inode, okay, because they're mostly within 10K. But for a small number of large files, you would have to extend this data structure, right, to become a multi-level data structure, a tree data structure, so that you can describe, it can describe large file size, okay? So this inode structure is extensible to grow if the file size grows, okay? So again, note the last entry here, right, is the inode, is a pointer actually to another inode. Okay, this is how you extend this kind of structure and to describe bigger files, files with file size bigger than 10K here. Okay. All right. So so essentially, the inodes, right, of the inodes allow the mapping of a linear list of blocks of data from a disk into what? Into a hierarchical structure. Okay? All right. As compared to this, file allocation scheme, so you have the inode structure, you have like a hierarchical structure. Again, this is a tree data structure. Okay? So in Unix, all the inodes, they're kind of numbered, okay, starting from 0. Inode 0 was always at a designated disk block, actually, allowing the Unix kernel to find the root of a file system. But by just knowing inode 0 where it is at, because inode 0 it has the Unix kernel, okay, to start from there, okay. Inode 0 in Unix is also a directory file, okay. In the Unix, you under the root directory, you see all those system directories like /usr, / bin, right, /tmp, right, and / dev. So these are like sort of under the root directory. You have all these folders there. Yes, Frankie, you have a question? You can just unmute yourself.
Yeah. How does the OS keep track of where the files start? Like at what block they start? Is it in the root inode?
Yes, correct. Each file has a root index node. Okay. Each file has a root index node. Okay. What I just talked about, inode 0, that's just the system, because like all inodes, they're indexed. Okay. They're called index node. Inode 0 is essentially your root directory under Unix. It's the inode 0 is for the root directory under Unix, but that's different from the root index node for each file. Okay, each file has a root index node. Okay, the file system knows the root index node for each file. Okay, what I just talked about, the root directory, right? The root directory under Unix is essentially the forward slash, right?
Okay.
We know each directory is also a file, right? So I was just talking about, for that root directory, its own root index node is inode 0.
Good.
Okay. And of course, each file has its own root index node. Actually, how do you find which index node corresponds to a particular file in Unix? you could just use ls-i, right? If you use this, then it will give you the index information, the index node information for that file. All right.
Gotcha. Thank you.
All right, no problem. Good question. All right. Any other questions? All right, let's continue here. Again, this is very important. Okay, this definitely will be this will show up in your assignment and your quiz. Okay. All right. So, well, I mean, where do we store the inodes? Right. We just talked about inodes. They're descriptors of files, right? So you do need to save those information, right? Those information, of course, they're also saved on the disk. Okay, so you can see, each file with this scheme, each file would cost you, an inode, at least one inode, right? Each file will cost you at least, right? At least, let me get rid of all this junk. At least an inode, right? Plus the actual data blocks for the file, right? So that means even you only have 1 byte for the file, for your file, you need to have what? At least 2 blocks, 2 data blocks for that file, right? 1 block is for the inode, the other block is for the file data block. So some optimizations of this scheme for handling very small files are, if the file size is very small, you could just put the file in the file information section of the inode, right? So if your file size is really small, you could just put the file here, right? The actual data of the file in the file information section of the inode, right? So that's one optimization, right? So you don't have to use another physical block just for holding that 1 byte, right? Actually, in Windows NTFS file system, this is one of the optimizations they did. Okay, so now inodes, they are usually allocated at format time. Okay, when you format your disk, right? First you do partition of your disk, right? And for a particular partition, you want to format when you format a partition, what do? You actually set up a file system for that partition, right? So usually at the format time, the inodes are usually allocated at that time. And all these inodes, they're usually put into known positions, okay? In the, here a little bit history on the Unix. In the original Unix file system, the first third or quarter of a disk was inodes, okay? That's in the original Unix file system. The rest were data blocks allocated to the files as needed, okay? So, and over the years, various file systems try to take into account the actual physical geometry of the disk by putting zones of inodes at different places on the disk. The BSD variation of Unix, they did that. Again, the NTFS uses similar kind of scheme, okay? All right, so now we talk about, this could be a hierarchical data structure, right? But when people came up with this scheme initially, it wasn't hierarchical, right? So if it wasn't hierarchical, then you would you would your inode could also become very large, right? Essentially, if this, essentially you just have to put, the index of the block, the indices of all the blocks, right? Here in the inode, pointing to the physical blocks. Okay, so that would be, so if you only have one level of inodes, essentially this is like a linked list, but you do have each block have an index, okay? That's still a key difference between the index node and the linked list. So this could be, so just to give you an idea, suppose a block again is 1K, okay, which is 2 to the 10 bytes, okay? So how many block pointers does an inode need to support a maximum file size of 16 gigabytes? Okay, let's say you want to describe a file with this size with, sorry, give me a second here. So you want to describe a file with a file size 16 gigabytes, right? So you have each entry here in the inode would give you 1 kilobytes, okay? So if you only use one level of inodes, like what would be this inode table size? Right? It would be what? You would need how, so 16 gigabytes, right? So essentially you would need 2 to the 24 kind of entries, okay? So you need that many entries, 2 to the 24th entries. Each entry corresponds to 1 KB, okay? Because 1 KB is what? 2 to the 10th, right? So this gives you the total of what? 2 to the 34. 2 to the 34 is what? Is 16 gig, right? So you need like 2 to the order of 24 entries in this one level of inode, right? Just for describing the data. So 2 to the 24 for each entry. If each entry, again, each entry here is like a pointer. Let's say each entry is 4 bytes. Okay. And what would be what? This would be 64 megabyte. Okay. So you need 64 megabytes just for describing the one file with this size. That's not ideal, okay? So we do need to look at the multi-level extension of this, okay? Now, the multi-level extension is not covered in the textbook, but we would like to cover the multi-level extension for this class. So you could see the multi-level extension in your quiz and assignment. Okay, as you are probably already thinking, this multi-level indexing extension is kind of reminiscent of the multi-level page tables in a virtual memory paging, right? So let's see how this works. Okay, so let's look at this diagram again. All right, so we talk about every file having a root inode. This is the root inode. Okay, it starts with file information of the metadata again. Then the first n blocks after the file information is what? The first 10 blocks. So they're pointing to what? They're direct pointers to the data blocks. Okay. Again, this n here in the Unix implementation, n usually is 10. Okay, so you have like 10 like pointers to 10 physical data blocks. Okay, then you would have a number of single indirect. What do we mean single indirect? That means each single indirect pointer points to another table. Okay, another table with each entry in that table pointing to a data block, physical data block. Okay. All right. So that's for single indirect. For double indirect is what? The double indirect is it would point to another table with each entry of that table actually as a single indirect. Okay. Now let's see another diagram here. This is the actual file system structure, a file system inode multi-level structure for Unix 4.1. Okay, so let me show you. So the first 10 blocks, the first 10 pointers, they're direct pointers to data blocks. Okay, and in Unix 4.1, it has one level indirect. One level indirect is what we call single indirect. Okay, and two level indirect is what we call double indirect. Okay, so the single indirect is what? It points to another, like I said, it points to another table. Each entry of that table points to a physical data block. Okay, for the double indirect, it actually points to a table of single indirects. Okay, and so each table, each entry in the single indirect table points to a single indirect table, and that single indirect table has each entry point to a physical data block, right? So that's what we call double indirect. Okay, and what about a triple level indirect? It would be this scheme. Okay. All right, so a single indirect, let's say you have n entries here. A single indirect would give you n data blocks. Let's say that, okay? So a double indirect would give you how many blocks, data blocks? Someone can tell me? So if a single indirect gives you n data blocks, what about a double indirect? A double indirect pointer here. What would this give you? How many data blocks would this give you? Anybody? Frankie, you have an idea? Or
Someone said
Jonathan? Yeah.
n
Yeah.
squared in the chat.
Yes. Yeah, Jonathan. Yes. Okay. All right. Thank you. All right. I just saw that. Thank you. Yeah. So n squared, right? What about triple? It would be n to the third, right? Power. Okay. All right. So let's see. So with this kind of setup, right? So let's say, you have this exact as setup here, right? What would be the biggest file size with this scheme? Anyone can tell me? Sorry, I didn't give you, I need to give you specifics, okay? So let's say each block has 1K bytes, okay? So N here is let me see here. Sorry, give me 1 second here. So, oops. So let's say each so each block is 1K size, and so first 10 data blocks will give you 10K, right? Right? And oops. So we're trying to find out like what would be this single table with this structure, right? What would be the biggest file size this can describe, right? So actually, let's look at this diagram here. All right. So this is the first 10 direct data blocks. Okay. And this would be the single indirect I just talked about. Okay. This would be the double indirect. This would be the triple. Okay. So each block has, we talk about each block is 1 KB. Okay, so this is easy for the direct data blocks. There are just 10 of them, right? So for this one, for the single indirect block, right? So this is just a block, right? So for the single indirect block, it has a size of what, 1 KB, right? So with 1 KB size, how many entries would there be would be there for this table for a single indirect block? Anybody can tell me? With each entry here occupying 4 bytes. Anybody can tell me how many entries would there be in this table for a single indirect block? So this table occupies a block, right? 2 to the 8th. That's correct. Yeah. Thank you, Jonathan. So 1 KB, right? 1 KB for this table, right? So that would be 2 to the 10th, right? Right? For the total size of this table. And with each entry occupying 4 bytes, right? You divide it by that. That will give you 2 to the 8th. Okay, so you have 2 to the 8th, 256 actually entries in this. Okay, so let's see. With this, let's see how big a file size this whole thing can describe. Right. So you have 10 direct blocks, right? Direct data blocks plus what? Plus here in the single indirect block, you have how many entries there? 256, right? 2 to the 8th. Right? Entries there, right? 256 blocks. That's what I meant there. Okay. For the double indirect block, how many entries are there? If a single indirect block has 256 entries, what would be the number of entries in a double indirect kind of setup? How many entries in total? There. Remember, let's go back here. It has what? So let's say this one has 256. So this is for the double indirect, right? It has 256, and each one of these 256 entries here points to another table that has 256 entries, right? So the total number of blocks a double or two-level indirect can describe is what? Is 256 times 256, right? All right, so a double indirect block here, that can give you what? 256 to the square, right? Not many data blocks, okay? Plus a triple indirect block would give you what? 3 levels, right? 3 levels is what? N to the power of 3. What is that? And then that's what that would be 256 to the power of 3. Okay? So if you add all these together, this roughly is 16 gigabytes. All right? So actually, give me 1 second. Okay, so actually this whole number, sorry, that's not quite accurate. So this, oops. So 10 plus 256 plus 256 square and plus 256 cube equals to what? The total number of blocks. Okay, total number of blocks that this scheme describes. Okay, so you need to use this number times what? Times 1 KB. Each block is 1 KB. Okay, and then that would give you 16 gigabytes. All right, any question about this? Is this hard to understand or? Anybody giving, anybody tracking? Yeah? Give me some response, guys.
Yeah, it's fine.
Okay, all right. Okay, so these are, like, by the way, I did put details in the slides if you guys want to look through how exactly I derived. So, so this would be here is how you do it, okay? So, so let's quickly talk about, so we just talk about how the inode file descriptor scheme is used for remembering and tracking file data layout on the disk, right? This is how the storage aspect of the file implementation. Now let's look into the file access perspective of this inode design, okay? So first is the sequential access. The sequential access would be like the linked list, right? So the blocks are, here the blocks are not necessarily contiguous, right? So you may need to jump from one physical part of the storage to another part of the storage, which could be very time consuming, especially for magnetic disks, right? As we talked about this the last time, due to the mechanical delays, we talk about, with magnetic disks, you would have the seek time and rotational time. Those are mechanical delays, right? So these data blocks, they can be in different locations on the disk. So you would have to jump between them. And also, as well as that's also true for the direct access. So the direct access is actually now a little faster, actually by a linear constant as compared to FAT scheme. right? So again, I list the FAT scheme here, right? So a direct access means you would want to access the file at a particular position and read from there, right? So in the FAT scheme, you would need to go through the file linkage chain to locate a physical position of the file, as we just talked about, right? So here you go to, file A starts from this position, you go to 7, and then you go to 2, here, and then you go to 10 here. So you would have to go through this chain, traverse through this, to locate a physical location of a file, right? But with the multi-level indexing setup here, okay, so you could do some quick computation actually to find which physical block corresponds to the file position you would like to access. Actually, today we probably won't have time for in-class practice, but probably we'll do it next time. So, but here you can, with this multi-level indexing setup, you could quickly, you can compute, with each block size, say at 1K, you can compute, for a particular physical location, for particular file position, you can quickly calculate which physical block would correspond to a location, a position in the file, right? But of course, in the multi-level indexing seek, it still requires traversal through the multi-level indexing structure, right? But this in general is faster than the linked list. All right. So let's quickly talk about the pros and cons of this scheme. Again, this multi-level indexing favors small files, as I talk about. So in the Unix the Unix file system designer, they kind of used that kind of stats, as I talk about. Most of your files in the system would be small files, so they expect one inode would be sufficient for describing one file. So most of your files probably would be within 10K of a size, right? Only if your files are bigger than 10K, then you would need a multi-level structure, right? So this kind of scheme favors small files. This is a very flexible kind of design, so it accommodates the incremental file growth very, very well, right? And it also, if you do assess this scheme by the performance of sequential and direct access, it can be efficient access, right? Because you can compute which inodes to read, and you can access data blocks with a small number of inode reads. Essentially, again, you can compute the physical location in the data blocks corresponding to the position in the file. Okay, so. All right, so, and actually some of the disadvantages of this is, so for the, for what I just talked about, the actually very small files, you could still, like a 1 byte file would still need 2 blocks, right? But there I talk about the optimization can be, you just put very small files into the inode, right? And indirect access, the random access is still, you need to traverse through the tree data structure for random access or direct access to very large files. All right. All right, so I don't know if we will have time for this for the in-class practice, and you guys will need to do this in the assignment and quiz, most likely. So, but I'm not sure if we have time for today to do this. So with about 10 minutes left for the lecture today, I do want to see if you guys have any questions about quiz 2 coming up on Thursday. Okay, let me stop the share here, and let me share the screen of the quiz 2 materials. Before I go through the quiz 2 materials, any questions about multi-level index allocation scheme? You guys were all tracking?
Yeah, it was pretty straightforward.
Okay, cool. All right, so all right, let me share the screen here. All right. Okay. I don't know why it's not sharing. Okay. Have any of you gone through the list of quiz 2 concepts? Do any of you have any questions? Here. Anybody? So we have, so we put together this list essentially, for what we talk about in the class for the virtual memory and paging system. I would say, the most important items here on this list would be what? Would be these, right? So you need to know. Give me 1 second.
Are the questions going to be like more problem solving questions similar to like on what we had on the assignment?
Correct.
Okay.
Correct. It will have a sort of, this I can tell you, it will have more computation than last time. Okay.
Okay.
So last time we sort of had a quiz that, you guys literally had to do like essay-like answers, right? So basically, this time, this quiz, you probably would have more questions that would need you to compute something and give quantitative answers. So last time it was more like qualitative answers, right? But we will have a combination of these. So you would need to, I would say the paging, right? So here the paging, the multi-level page tables, how exactly they work, how you set up paging, right, for one level or for multiple levels. How do you compute? You need to be familiar with all those terms, right? What's the page size? With a particular page size, how many entries you would have for a page table, right? And then you need to do some translation, right, for a virtual address to a physical address, and all those kind of stuff. So you guys did that in the assignment and as well as in the programming, right? So you need to be proficient in that. And others would be, yeah, so we would also have probably some definition, some questions that would ask you for definitions of concepts, and maybe some scenarios that you would have to analyze and give qualitative answers. Any other particular questions? And also, I would say the page replacement algorithms, that's also, you can see it's very good test material, right? So, all right.
So this covers everything from the last quiz up to semaphores then. Not, it doesn't include semaphores, but everything in
Doesn't-
between.
Right,
Correct?
exactly, yes. Yeah, so essentially just memory management, virtual memory and paging, everything related to that. All right, so you guys can see my slides, the PowerPoint. It's actually literally I had everything there, right? And things like if like we talk about, like, just look at your assignment, what you did there. We also talk for some calculation about effective access time, right? With address translation caches. Address translation caches, they're what? They're called translation look aside buffer, right? So with that, what would be the effective access time? So yeah, again, it would be probably 5 questions. We haven't finalized everything there yet, actually. So, but I would, again, I would suggest the same as the last time, probably by just looking into the textbook as well as the slides from the class, you probably would find answers quicker, right? Instead of searching the internet, right? So you're not supposed to search the internet, but we can't control that. But I'm just saying, you can essentially searching the slides and the textbook maybe will give you quicker answers. Okay. All right. Any other questions? You guys are pretty confident, seems, for virtual memory paging. Well, you guys did a lot of practices like on how to compute for virtual memory paging, I guess, in your assignment as well as in your programming portion, I guess. But do get yourself familiar with, again, everything there, right? So I think you guys should do well. All right.
Cool. Thank you, Professor.
No problem. Okay, so we're out of time. So next class we will continue. Well, next class you guys will have the quiz, and the class after that will pick up what we left off today. Okay. All right. Thank you, guys.
Thank you.
Okay. Bye.